Welcome back. In this second part of the screencast, we will be talking about the gradient. One of the most interesting directional derivatives to study is the direction of greatest slope. This can be found using the gradient. The gradient of f, written del f, and read del f, or written grad f, is the vector defined by del f equals fx times I plus fy times j. Del f is a vector in the plane, not a vector in space. So this gradient points in the direction of greatest slope, but it is a horizontal vector. We can see an illustration here. We'll see maybe a better illustration on the next slide. This is our surface. It seems like it's curving. The direction of steepest slope would be somewhere in this direction. The gradient is a horizontal vector in the xy plane, but it does point in the correct direction. The directional derivative can be written as a dot product du f equals del f dot product vector u. So here's an illustration where we'll see a little bit better what the gradient is. On the left we have this mountain here, and at this point the direction of steepest slope is probably this direction here, and the gradient points horizontally in that direction. So it's not easy to see. It's a green vector that points straight in the mountain. If we look at level curves, this is what it looks like. So it's perpendicular to the level curves, as we'll discuss later as well. This feels too bad, like we would want the vector to be in 3D and it would tell us basically the slope of the tangent plane if the vector was going up here. Well, actually, it tells us the slope. That's the genius about it. The magnitude of the gradient is the slope of the tangent plane. So basically, the magnitude of the gradient tells us how steep it is to walk up. So here are three properties of the gradient that we will prove. Let f be differentiable at the point xy. If del f equals 0, then all directional derivatives equal 0. Let's see how we can prove that. If del f is equal to 0, note that this is a vector 0, unlike the directional derivative, which is the scalar 0. If del f equals 0i plus 0j, then if u is any unit vector, clearly using the fact that du is the dot product of del f and u, we have du of f equals del f dot product u equals 0. It makes sense because del f is the magnitude of del f will tell us the steepest slope. So if del f has a magnitude of 0, the steepest slope is 0, and therefore all slopes are 0. The second property is this. The direction of maximum increase of f is given by del f, and the maximum value of the directional derivative is the magnitude of the gradient. So we've said that a few times, now we're going to prove it. So given that the directional derivative is the dot product of del f and u, we can use the definition of the dot product. It's the magnitude of del f times the magnitude of u times cosine phi, where phi is the angle between u and del f. Now remember what we said in the first part, u is a unit vector and therefore the magnitude of u is 1. That brings this little expression to magnitude of del f times cosine phi. So how can we choose u to get the greatest directional derivative? We want cosine phi to be as large as possible, and that will happen when phi equals 0. The maximum value occurs when phi equals 0, which means the maximum slope, the maximum directional derivative will happen when we choose a vector u that is parallel and in the same direction as the gradient. Which means when u is parallel and in the same direction as del f. Moreover, we can see that the maximum value of the directional derivative is the magnitude of del f. What about number 3? Number 3 says basically the opposite of number 2. The direction of minimum increase of f is given by negative del f. The minimum value of the directional derivative is negative the magnitude of del f. The proof is exactly similar. We have the magnitude of del f times cosine phi that yields the directional derivative, and just the same as before, this time the minimum value occurs when phi equals pi, which is when we choose a vector parallel and the opposite direction of del f. This will yield cosine phi equals -1, and therefore the minimum value we can get for du f is negative magnitude of del f. So, a couple of notes to conclude this second part. Remember that del f is a vector in the xy plane, and remember that del f carries two information. Firstly, it points in the direction of steepest slope, but horizontally. And secondly, the magnitude of del f yields the slope of the tangent plane to the surface. Okay, so here you can either move on straight to this third part, or you can do these exercises from the textbook to practice the concept we just studied now. Thank you!